Hello! Today I want to talk about monads. So you might remember monads from programming in Haskell, or maybe from the coursework, but today we're going to see what a monad is in category theory, which is where they originally come from. So let's start with Haskell. So we'll fire up JTI, and then if we ask what a monad is here, see that it's a class of certain things, and it has to be applicative. And if you look up what an applicative is, then we remember that it's a certain kind of functor. So we know what functors are in category theory. We don't know what applicatives are, but let's not worry about this today, although there is a fine answer here as well. But if we ignore that middle layer, then we see that a monad is a certain kind of functor, right, which comes with some extra information. And the important things here are the return and the bind. So if you're thinking of these things as effectful operations, then the return says that if I have a pure thing, then I can embed it as a trivially effectful thing. And the bind says that if I have a first thing that I think of as I run this, then I get some value out, and based on this I determine what to do next, and that's going to be my overall thing. And this is what's underlying the do notation that we have been using as well. Right? So that's fine from a programming perspective and very useful, but let's see if we can see what this looks like from a category theory perspective. And then this bind is a little bit cumbersome because we have these two arguments, whereas in category theory our morphisms only have one argument in general, right? So we could ask for product, so we could ask for something called a function space in our categories, but we don't have to, because we can actually give an alternative definition of this bind that's equivalent. So the first thing I'm going to do is I'm going to just flip these two arguments to make it a bit clearer. So if I define a variant of bind, which is just a flip of bind, if I look at the type of that, then you see, oh, I flipped the wrong thing. Right, then you see that all that's happened is that now it looks more like some kind of function transformer, right? So I get in a function like this, and I get back one out where my codomain, where my domain is also m of a rather than a. So if I have that, and I now choose a to be m of b, and this function here to be the identity, so I do a flipped bind of the identity, then I get something of this type out, right, where I get two layers of effectful things, and I join them together to get one layer of effectful things. So if I have a monad according to Haskell, then I can always define this join. But conversely, if I have this join, then I could also define an alternative bind by saying that the bind of f is first I f map f. So f here goes from a to mb. So if I f map that, that goes from ma to mmb. So then I have an mmb, and I can use the join to collapse that down to just one mb. Right? So I compose this with join like that. And if I ask for the type of bind prime, and I say that I have something again which is like the flipped bind. Right? And you can show that with the right laws, then these two operations are actually inverse. So these are equivalent ways to phrase being a monad. But the advantage of this one is that this one now makes immediate sense in any category, right? Because we are asking for a morphism of this type. So if we do that, so I want to switch over to my fake whiteboard, then you can say that a monad is given by, first of all, a functor m, which goes from C to C, where C is a category, and then we want to return, which we often write as eta, because we're trying to be fancy. So this eta x should go from x to mx, right? This is our return. And another way to say that is that eta is a natural transformation from, this is the identity applied to x, and this is m applied to x. Right? So this is natural transformation from the identity functor to m. So we often write a little dot like this to talk about natural transformations. Okay, so that's our return. And we also wanted to join, which we often write as a mu for multiplication, but that's another story. So this should go from mu at component x, we go from mmx down to mx, right? Which in other words means that mu is a natural transformation from m composed with m down to m, right? And it's important that these things are natural, because this comes up in calculations, but we also need some additional laws for these things, just like we have the monad laws in Haskell, right? So the first law that we want is that if I start from mx, then I could always return this with eta mx, which gets me 2 layers of mx, and then I could join it back down again with mu. So I'm taking something I'm thinking of as maybe effectful, and then I'm making it trivially effectful at 2 layers, and then I'm joining them together. But because eta is not really adding any effects, I shouldn't really do anything by making them collapse down to 1 layer again. So this should just be the identity. So I want this diagram to commute. So I want this to be the identity here. And similarly, if I start with mx and I look at eta, which goes from x to mx, and I apply m to it, so I'm using the functorial action, that's m of eta x, and then I go down and collapse it down to mu again, then again this should be the same thing as doing nothing. Because again, this eta is not really adding anything, so it doesn't matter. It's just a fake effect, so to speak. And finally, if I start with 3 m's, like this, then there's actually 2 ways I can go down to 1 m, right? So I could either look at mu at mx, so this is my inner thing, and here I have 2 m's. So I'm going to collapse those 2 m's into 1 m, and I still have my mx here, and then I can collapse this with mu of x, or I could look at mu at the inner thing, and then, so that's just the mu, going from here to here, and if I now apply m to it, that's going to stick an m on the outside of both of these. Right. So that's like doing the mu on the inside, this is doing mu on the outside. And then here again, I can do another mu to collapse this. So these are the 2 ways I can go from here to here. Right. And I'm asking that these 2 ways are actually the same, so this diagram actually commutes. Right. Okay, and here is just all of this again, but written in Agda. So I said that a monad on a category C is a functor from C to C, and then I'm just naming this functor m privately in this definition, so that is not so long. And then I'm asking for 2 natural transformations, one called return, one called join. Return goes from the identity to m, join goes from m composed with m to m. And then here I'm naming these, the transformation part of this, so that it's easy to state these laws, and they're exactly the laws that I just showed you, right? So this one is return before join is the identity, fmap of return before join is the identity, and these are the 2 ways of joining 3 m's down into 1. And finally here I'm opening the functor part of m publicly, so you can use the action of the functor without adding an extra layer of indirection.